In other words, what does it mean to make a digital signature or a digital proof vanish? Right? So the way we think about this is with making the soundness of the proof or the soundness of the signature disappear over time. So consider Alice, who signed something at time t is equal to 0, and we want the signature to be sound up to time t. But then after time t, it shouldn't be sound anymore. A verifier looking at the signature wouldn't be convinced that it's Alice's. So this also gives us a notion of deniability. If someone sees the signature after time t, Alice could possibly claim that she never signed it. It could have been made by someone who had no knowledge of her private key. Right. So how do we do this? The underlying technique behind all of our constructions is to allow for signatures to be forged through a slow computation. And similarly, proofs can be forged like that. So here we have a forger who does a long sequential computation of these steps and finally produces a forgery. And to any distinguishers seeing the real signature by Alice and the forged signature, they're indistinguishable. All of this requires some notion of time. So someone getting a signature should know if it was made within the past time or not. And it's hard to timestamp every single signature, but it's not even possible. So without like a global clock or anything. So what we use instead are beacons. So consider like a global beacon over here, which emits some bits of randomness every delta steps or time over here. And this randomness is unpredictable, uncontrollable. So beacons have been made using randomness from stock prices, blockchain block hashes, and distributed protocols with multiple parties like DRAM and so on. So how would a solution with a beacon look like? If, say, the beacon value B was emitted at time 0, and we want the signature or proof or whatever was created to expire at time t after the beacon was released. So here, say Alice signed something after the beacon was released. The signing algorithm that Alice uses would specify the beacon value in the protocol, and similarly for proof. And once time t is reached, regardless of when exactly Alice made her signature, the soundness would be lost over there. Right? So without a timestamping mechanism or a global clock, we can use beacons to make signatures expire after this. I want. Yeah, so in the rest of the talk, I'll go over some applications of short-lived proofs and short-lived signatures, and I'll then go over constructions which use verifiable delay functions as a key tool, and I'll briefly go over them. Okay, so in deniable email, so when email servers exchange emails, they sign outgoing emails to authenticate them. So this is required for security, and it's only really needed during transit. So when the second server receives the email and verifies the signature, it's no longer needed. But these signatures do last forever, and undesirable side effect of this is that they can be used to validate things. So here's like a picture of a famous WikiLeaks email dump in 2016, where all of the emails were actually kept their Google signature with it's called DKIM, domain keys identified mail. So this is not at the intended use of these signatures, and this problem was popularized by Matthew Dean, and where one solution he suggested was Google would like periodically release their signing keys every month or so, it'll be public, and so any signatures made under those. So short-lived signatures are like a natural solution to the problem, where when an email server wants to send an email, they sign it with a short. It'll be valid for like 2 minutes until it's reached and verified, and so it serves its purpose. And then after that time, it becomes invalid. So over here, you could show the signature after time to the whole world, and anyone could have made it. Right? And with this, the advantage here is that the signer no longer has to do any actions like releasing their key. They can keep one key, and they don't have to cycle keys or anything. So if you like your private key, you can keep your private key. If for short-lived proofs, like the reboarding system, So suppose someone makes a vote ballot box, and the ballot box gives them their proof that their vote was included correctly. Right? An undesirable side effect of this is that this proof can be used to get like and it's like a receipt of what they did. So e-voting systems want to have like a receipt property. So this is a short proof. The proof lasts for a few minutes while they're in the ballot booth, and after that, it loses its meaning, so they can't. It doesn't function as a receipt. So there have been lots of related work on this area of deniable cryptography. For example, like designated verifier proofs are proofs that make sense to one verifier but to no one else. But we move to like more of a time-based setting where it makes sense to everybody before time t and time signatures. I heard of time signatures or time capsule signatures. We gotta solve the inverse problem of this, where for them signatures are like locked until time t and valid afterwards, where we want signatures to be valid before time. Keyforge and Timeforge solve the deniable signature problem, where they also use actions from the signer or a third party to give deniability. Proof of work or knowledge also solve a problem where someone either knows a witness to a proof or did a long time, but they use proof of work and it's parallelizable and not really a notion of time. Okay. So just a quick note on formalizing short. So in the rest of the talk, I'll stick with short-lived proofs. So in formalizing them, they have like a prove algorithm and a verify algorithm. Additionally, they have a forge algorithm, and all of these take the beacon value. And completeness is that the proving time should be the forgeability, the forging time should be just over t. Indistinguishability means that the proofs generated by prove and verify forge. And this gives us clear knowledge because forge can. And we need a new notion of soundness called t-soundness, where you can extract a witness from a prover that can produce proofs in time less than. But after time t, this extraction guarantee is lost. So all of our constructions will be transformation from a generic or a protocol into the short-lived version. We have 4 transformations of proofs in our paper and 2 more. I'll briefly go over the and key clue in all of the constructions. So a VDF is a function that takes a fixed number of sequential steps to compute. But once this computation is done, it's easy to convince a verifier that the computation was done correctly. So here, an example are repeated squaring VDFs, where the input is an element in a group of unknown order, and the output is y. And the fastest calculating. But once these steps are done, they can generate a proof that convinces the verifier that y is indeed equal to x. So the way we present it is we need to consider like videos efficiently. Just suffices to know that a video. The security property underlying the VDF is that it's hard to convince a verifier without spending time. Okay, so the most straightforward construction to get a short-lived proof is just to take the or whatever relation you want to prove and just verify. If you have a relation R with input X and witness W, that's one branch of the OR, and the other branch is the VDF verifier taking the beacon value. Right, so this satisfies completeness because an honest prover can ignore the VDF branch and just satisfy the relation branch with the witness. And a forger who doesn't know the witness will have to satisfy the VDF branch by actually computing the VDF. And since the VDF takes 3 steps to do, you get we also prove indistinguishability and soundness. Note here that only one person has to compute the VDF output and proof on the beacon value, and everybody can use their Y and pi to forge proofs on any relation. Right, so this stronger notion of forgeability we're calling reusable forgeability, where the first forger additionally produces an advice that helps make more forgeries. So here, this is really good in practice because one long computation for beacon value can help generate multiple forgeries. And the more forgeries there are, the higher the reliability for a single it enhances the reliability. For the main constructions, we are going to transform Sigma protocol. So just to establish encryption, you have a Sigma protocol for relation R with input X. And the first step of the Sigma protocol A gets a challenge C and sends it on C. So the proof is ACC. And Sigma protocols have a simulate function where without knowing the witness, you can simulate a realistic that is verify X. So how do we make a Sigma protocol structure? So the first step over here, we're going to split the challenge into C1 and C. And what we're going to do is use what we're going to do is use C1 as a challenge for the relation Sigma protocol, and C2 as a challenge for the VDF verifier, where C2 XORed with the beacon value will be the VDF verifier. Right. So why does this work? The intuition is that the forger and the prover will each beat on different branches of this and honestly complete the other branch. So the forger can simulate the relation branch, but then they'll have to honestly complete the VDF branch by solving it. And the honest prover can cheat on the relation branch on the VDF branch by using but then they'll have to honestly complete the relation branch, which will complete the witness. So that's the intuition behind this. I won't get into the details of the protocol. Just want to note here that the input to the VDF verifier is not just B, but B XORed with it. So we don't get reusable forgeability like in previous. So to get reusable forgeability, we design a new type of VDF called zero knowledge VDFs, which are similar to VDFs except that the output Y isn't revealed. You have again like if you're sparing VDFs, you have X and you can do Y. But you just give a proof that you know Y. You don't have to reveal Y, and it can verify that you do know the output of the VDF. The neat thing here is that this could actually be represented as an efficient Sigma protocol with a first method and it has a nice simulate algorithm where without knowing the Y, the output Y, you can simulate a realistic looking transcript for this. We build efficient zero knowledge VDF using the proof and algorithm and so now that we have a ZK VDF as a protocol, we can use the classic Sigma OR composition of the relations Sigma protocol and just like Sigma OR compositions, you can simulate one branch and honestly complete the other. So the prover can simulate the ZK VDF branch without actually, and they can run the Sigma or the relation Sigma protocol using the witness. But the forger, since they don't know the witness, they'll have to simulate the relations branch and then honestly complete it. So we get complete. And the nice thing here is that the VDF branch is just value, so it helps that only one person has to complete the VDF branch, and it makes other folks. We have more efficient constructions, particular for signatures, which use different VDFs called trapdoor VDFs and one of which has reusable forgeability as well. And just briefly going over the implementation, we use Veslovsky VDFs, which with RSA 2048 groups, which are pretty large. But even with that, the overhead for transforming Sigma protocol into a short-lived Sigma protocol is pretty low. It's only like half a kilobyte for the proofs and even less than that for RSA signatures. And the prover time overhead is 120 milliseconds for the prover, which is not that much, and much lower for the signature algorithm. So just wanted to highlight here that these transformations are practical and efficient. Right. So with that, I'd like to conclude and I'd be happy to take any questions. Thank you.
Any questions? I have one. How fine, how fine grain can you control the period of the time?
Yeah,
Does that period depend on the beacon?
it's actually dependent on the VDF. So here our VDF is y is equal to x power 2 power t, and it takes exactly t steps to compute. So the practical time would depend on the proving hardware and all that, but the VDFs are becoming very standardized with like a specific ASICs to compute this. So it's likely that it won't get any faster beyond a point. Like there will be fast hardware that does it really fast. So we'll have to, that'll probably be the benchmark for the actual physical time that it takes. But yeah, this number of theoretical steps is fixed, but the hardware depends on the hardware.
Other questions? Any?
Hi, thanks for your talk. So I just have a quick question. So are there any technical difficulties when extending from Sigma protocols to multi-round protocols?
Yeah, we haven't thought about that, but yeah, that would be interesting because for us, if they can be composed like if they have a composition available, I think it would be easy to do. So that might be the underlying thing. You can always try to compose with the VDF and the original Sigma protocol. So that's, I think, it will come down to that.
Okay, thanks.
So yeah, that's interesting. You think about it.
Okay, so let's thank the speaker again. The second talk in this session is rotatable zero knowledge sets, post-compromise secure auditable dictionaries with application to key transparency. And the speaker is Eli Goldin. Please go ahead.
Hello, everyone. I'm Eli, and I'm going to be talking about rotatable zero knowledge sets. This is joint work between Zoom, NYU, and Microsoft Research with Brian Chen, Yevgeny Dodis, Isha Ghosh, myself, Alexander Kasavan, Antonio Marcedon, and Mariam Bermau. Our motivation is for end-to-end encrypted communication systems, whereby parties want to communicate securely with each other. All messages must pass through some untrusted server. This is typically done using public key encryption, but the problem is that users need some way to agree on each other's public keys. If, for example, the user were to host a database of public keys, if, for example, the server were to host a database of public keys, then this could lead to man-in-the-middle attacks, whereby the server could respond with a compromised public key. To prevent this, the most common solution is to use security codes, whereby users will send each other directly a QR code that can be used to verify that the public key returned by the server is in fact correct. This is tedious and requires manual verification. And so it can be automated with something called a key transparency system, otherwise known as an auditable dictionary. In a key transparency system, the server will provide a commitment COM to the database of public keys. And whenever a public key is queried, the server will, in addition to the public key, provide a proof pi that the given identity public key pair is in fact in the committed database. Note that we also require a uniqueness property. That is, for every identity, there should be at most one public key that can be proved to be stored in the database. Then, as long as all users agree on the commitment, man-in-the-middle attacks can be detected by users verifying that their public key is stored correctly. The database may also update, and perhaps frequently, as users update their public keys. And we would not necessarily want users to have to check that their public key is stored correctly for each commitment. So every time the server updates the commitment, it will also produce a proof pi that the update has been done consistently, which can be independently audited, not by the users themselves, but by some trusted third parties. And this increases the efficiency as users no longer need to check that their public key is correct every single update. By default, this does not preserve privacy. That is, the proofs may leak information about the database, but there are privacy-preserving solutions for key transparency, namely Connix and Seamless as examples. I will be focusing on Seamless since that is what our contribution builds off of. Seamless achieves private key transparency using a primitive that they call append-only zero knowledge sets. An append-only zero knowledge set, or AZKS, is essentially a key transparency system, but for generalized databases for any label value pairs. The consistency property that the proofs verify is that the database is append only. That is the proof, the update proof shows that no database entries have been either deleted or changed. The proofs in AZKS are privacy preserving, that is there is zero knowledge. The proofs, both query and update proofs, reveal no more information than necessary. And it turns out that to achieve AZKS, the construction in the Seamless paper really requires some sort of secret key, public key primitive, and that is the database. The server storing the database will also have some secret key that they will use to hide the data, and there will be a published public key that will be used to verify the proofs. Note that Seamless and neither Connix or any existing key transparency system satisfies post-compromise security. That is, if the secret key is revealed during, say, commitment 1, then for all label value pairs, including those added in later generations, privacy will still be lost. Our contribution is to add post-compromise security to private key transparency systems. In particular, we define a new primitive called a rotatable zero-knowledge set, which is the same as append-only zero-knowledge set with an addition of a rotate operation, which will change the public key and provide a proof that the rotation has been done correctly. The idea is that even if the old secret key is compromised, all label value pairs under the new private key will maintain private. Let me begin by talking about a basic construction of key transparency systems without the privacy guarantee, and I'll show that how Seamless extends on this to add privacy, and then our contribution on top of that. So the basic contribution is that the commitment to the database will be the root of some sparse Merkle tree, where for every label value pair in the database, there will be a leaf corresponding to the value at the index at the point indexed by the tree path corresponding to its label. Then a label value pair can be proven to be stored in the commitment just by giving the Merkle opening. Note that this does not maintain privacy, as if, for example, the Merkle opening contains some other leaf, some adjacent leaf, then it will reveal the fact that the corresponding adjacent label value pair is stored in the database. To add some privacy onto this, the first thing Seamless does is replaces the value stored at the leaf with a commitment to the values. This then does hide the privacy of the values. And in fact, and so now the new opening for the commitment will be the Merkle opening, as well as an opening for the leaf, the commitment on the leaf. But note that this still does not achieve total privacy, since if there is an adjacent leaf, it will reveal the fact that the adjacent label is stored in the database for some value, even though it doesn't leak the value itself. So we know that we need to, so the first approach, the approach that Seamless will use, is to replace the label indexing the leaf with some other value associated with the label. Note that this cannot be deterministic, as then it will leak too much information about the label. But we may hope that, okay, what if we replace this path with, say, a commitment to the label? This is getting close. This does preserve the privacy, but the problem is now we lose the uniqueness property. That is, for one label, there may be two commitments that correspond to that label. And so therefore, as if there are two commitments, then there may be two values stored in the database corresponding to the same commitment, which would be a problem. But so we know that we want some randomness in this path, but we need also uniqueness. So the correct approach, it turns out, is to use something like a PRF, which will guarantee that there is only one PRF output for each label, but will still maintain the privacy of the label itself. The problem here, the problem with just using a PRF directly, is that there is no way for verifiers to tell that the Merkle opening, in fact, corresponds to the label. That is, there is no way to associate the output of the PRF on a label with its input. So the key trick that Seamless uses is to index instead with the VRF, with a VRF applied to label, or a verifiable random function. Intuitively, VRF is just a PRF where you can prove that an output corresponds with its input. More formally, a VRF is a triplet of algorithms, keygen, query, and verify, where keygen outputs a secret key, public key pair. Query takes in a secret key and some input and gives an output and a proof pi. Here I'm going to call the output of the VRF the box containing X for visual reasons. And finally, verify will take in the public key, an input and an output, and a proof, and output 0 or 1. The two security properties we require are uniqueness, that verify should output 1 if and only if y is in fact the box containing x, and pseudorandomness, that is the box containing x should look random as long as the secret key is not revealed. Note that pseudorandomness should still hold even if query proofs for some other inputs are given. So to add key rotation onto seamless, we are going to do the simplest possible thing, which is we will come up with a new secret key and public key and completely rebuild the Merkle tree from scratch. This works since new label value pairs are going to be under some completely new secret public key pair. But it remains to be shown how to prove that this rotation is done consistently without revealing information about the database. What this boils down to is that we have two sets of VRF outputs, and we need some way to prove that they come from the same set of inputs. And so to do this, what we do is we define a new primitive called a rotatable VRF, which will have this property that you can produce these rotation proofs, and we will show how to construct it. More formally, a rotatable VRF will be a VRF with two additional algorithms, rotate and varrotate. Rotate will take in a secret key, as well as some set of inputs, produce a new secret key public key pair, as well as a proof of rotation. And varrotate will take in two public keys and two sets of outputs under the corresponding public keys, and output 0 or 1. Intuitively, we want varrotate to succeed if and only if for each I, yi corresponds to, say, the blue box containing x, I, and yi prime corresponds to the green box containing xi. And also, we want to model post-compromise security. That is, the green box containing x should be pseudo-random even given the old secret key. To model more formally our security, we're going to strengthen the security of the underlying VRF and build up on top of that, just because the stronger security requirements on VRF will make it easier to add more complicated definitions or more advanced definitions. We're going to strengthen uniqueness and extractability condition, which I will not talk in detail about here. And we're also going to strengthen the pseudo-randomness requirement for VRFs to a zero knowledge condition. That is, the proofs for the VRF should be simulatable, even if the output of the VRF is replaced with the output of a truly random function. Then, to define rotatable VRF security, we're just going to combine this post-compromise security property into the zero knowledge requirement. More formally, we're going to model zero knowledge as the idea that a real and ideal game are indistinguishable. And in the real world, we can imagine some Alice interacting with a server hosting a VRF as follows. Alice will receive a public key at the beginning and can make any number of queries to the VRF. Alice may ask also that the server prove that some correct input-output pairs of the VRF are in fact correct, and may ask for rotation proofs, where Alice will pass in some set of inputs, and the server will provide the new public key, as well as a proof that the rotation was correct. Note that implicitly, the server will also receive the VRF outputs on both the old public key and the new public key. And finally, to model post-compromise security, we allow us to make corruption queries, which will return the current secret key. In addition, we also model some idealized object, or perhaps a random oracle or generic group, and we allow Alice to make queries to the idealized object. To define zero knowledge will state that this world is indistinguishable from the world where all these oracles are replaced with a simulator, even when the VRF outputs are all replaced with the outputs of a truly random function indexed by the public key. Note that to model that rotate proofs do not reveal anything about the inputs. We require that the rotate proofs be simulatable, only given the VRF outputs under both the new and old public keys. To make this possible, the simulator has three capabilities. First, it can control the initialization of the public key. It has full control over the idealized object, that is, it can program the random oracle. And finally, whenever a corrupt query is made, the simulator will gain access to all queries made to the random function. This is to model the idea that once the secret key is revealed, the VRF should no longer be pseudo-random. Before I get to our construction, I'll give a brief preliminary on DDH tuples. A DDH tuple is a 4-tuple of group elements, G, H, G to the A, H to the A, where the last two elements are the first two elements raised to the same exponent. Chom Peterson in '93 show how to give a zero knowledge proof that a given tuple is a DDH tuple, and this can be made non-interactive with the Fiat-Shamir transform. Our construction for rotatable VRFs will be based on a standardized construction of VRFs pushed forward by both Seamless and NIST. This is an efficient and simple construction, and our addition will be also simple. So this really is useful for practical purposes. In this simple standardized construction, there will be a random oracle F from the message space to some group, as well as a group generator little g. And how the construction will work is that keygen will sample a secret key uniformly at random, and the public key will be equal to g raised to the power of the secret key. Then the VRF output on some input x will be the random oracle applied to x raised to the power of the secret. To give a query proof, to give a proof that some given output corresponds to its input, all that will be necessary is to give a proof that g f of x pk y is a DDH tuple. Why does this work? Well, if this is a DDH tuple and the public key is equal to g to the secret key, then that definitely means that the output y will be equal to f of x to the sk, which is exactly the same as saying that y is the VRF applied to x. This satisfies all the VRF requirements and satisfies both uniqueness and pseudo-randomness, and works totally. To add on to this, we then define the rotate algorithm to simply sample the new secret key and public key uniformly at random. That is, the secret key will be sampled uniformly at random, and the public key will be set to G to the SK, just as before. We will model this for purposes of the proof by saying that the new secret key will be the old secret key times some randomized exponent A. And the reason that this is nice is because this means that the new public key will be equal to the old public key raised to the A. But this is exactly the same as just sampling the secret key uniformly at random. Then, to provide a rotate proof, all that we do is provide a proof that the public key, as well as the first output and the second public key and the second output, is a DDH tuple. And why does this work? Well, if the first output is the output of the VRF under the first secret key, that is if y equals f of x to the sk, and if the second public key is the first public key raised to the a, that is pk prime equals pk to the a, then that means that y prime must be y to the a, which is the same thing as the random oracle raised to the secret key times a. But since the new secret key is the old secret key times a, this is exactly the same as saying that y prime is the VRF applied to x under the new secret key. And ignoring rotations under the DDH assumption and programmable random oracle model, this VRF is zero knowledge, satisfies zero knowledge. And the idea behind this proof is that you can program the random oracle so that the randomized output y equals f of x to the sk. So once we know the randomized output and the secret key, we can choose f of x so that this all works out. But the problem is that this proof approach no longer works once we bring in rotations. And the reason for this is that if we say publish two public keys, pk and pk prime, we are going to informationally, theoretically, commit to two secret keys. Then, after we publish these public keys, we may get some input x queried to the random function. And so we'll get some uniformly at random chosen y and y prime. And we're going to need f of x to satisfy both the equation f of x to the sk equals y and f of x to the sk prime equals y prime. Since the public key information theoretically commits to the secret key, and x is going to be chosen after the public keys are chosen, these equations may be impossible to satisfy just by programming the random oracle. So what does this mean? This means that the proof approach for the standardized VRF does not apply when we're dealing with rotations, but that doesn't necessarily mean it leads to an attack. And we tried for a bit and we could not find anything. So what we managed to do is we show that this rotatable VRF is in fact zero knowledge under a stronger idealized model, namely Shoup's generic group model. In Shoup's generic group model, our parties are given access to a random oracle EXP modeling group exponentiation, as well as an addition oracle star, which takes two outputs of the EXP oracle and multiplies them as if it were actually group exponentiation. Importantly, we allow our simulator to program the generic group, just as it could a random oracle. The key trick is that in the generic group model, giving out the public key does not necessarily commit to its discrete log. That is, we don't need to define discrete logs until a corruption happens. And when a corruption happens, all queries are revealed to the simulator. This means that we can choose the secret keys after we find out the uniformly random y and y prime. Now I'll go through a little bit more formally what exactly the simulator do when keeping track of the generic group. So we can think of this EXP oracle as really a table of group elements in discrete logs, where each group element corresponds to some value tracked by the distinguisher Alice. So what our simulator will do, the key trick, is that we'll replace the discrete logs with a uniformly random number with polynomials and some special variables. And in particular, discrete logs will be stored this way for group elements that do not come from the EXP oracle, like the output of the random oracle and the public keys themselves. So the variables that we will use is we will set that the output of the random oracle will always have discrete log, a variable corresponding to its input. That is, the output of the random oracle, f of x, the group element corresponding to that, will have discrete log, a variable b of x. And similarly, we will create new variables for each of the a's from the rotation proofs. And in particular, pki will have discrete log, the product of a1 through ai. Then, once we have set the public keys and random oracles to have these discrete logs, we can make sure that the output of the VRF has corresponding discrete logs. That is, the output of the VRF under some public key and some input should have discrete log equal to the product of the discrete log of the public key and the discrete log of the random oracle of that input. We can then define all other addition queries made by the distinguisher to be consistent with what we set the discrete logs to be for these other variables. Then, when a corrupt query is made, we will simply replace each of these AIs with a value chosen uniformly at random. And then we will return that the secret key that has been corrupted will just be the discrete log of the current public key. And what this guarantees is that the output y that is supposed to correspond to VRF of the secret key on x will be equal to f of x to the sk for all sk and x. The key idea here is that the degree of these polynomials only increases on rotation. And since the only issue that could occur really is that sampling these AIs induces the collision on the polynomials. And since the polynomials have bounded degree, the Schwartz-Zippel lemma tells us that a collision will happen with negligible probability. And so this works. So in conclusion, using this generic group model polynomial programming technique, we show that rotatable VRFs satisfy zero knowledge. Rotatable VRFs then give us post-compromise secure auditable dictionaries, in particular RZKS as we define it. There are many additional subtleties and small improvements in both parts. So for more details, read our paper or feel free to come talk to me afterwards. Thank you.
Questions?
Hey, have you thought about like how this would work for pairing-based VRFs?
Pairing-based?
You
For
can kind of use,
pairing-based VRFs?
yeah, you can kind of use the same construction as a VRF with a pairing group, and then kind of verify with the pairing.
I have not thought about it at all, but come talk to me afterwards and we can discuss.
Yeah.
Okay, then let's thank the speaker again. Okay, the final talk in this session is by online. Okay. The title of the talk is DAG Sigma, a DAG-based Sigma protocol for relations in CNF. The speaker is Gonjan Zhen. Gonjan,
Okay.
are you ready?
Yeah, I'm ready. Can you hear me?
Please proceed. Yes, we can hear you.
Okay, please allow me start it. Okay, thank you for attending this talk. This is Gongxian Zheng. Today, I would like to present my paper, DAG Sigma, a DAG-based Sigma protocol for relations in CNF. Other co-authors are Junzuo Lai, Zheng Huang, Yu Wang, and Zhiming Zheng. The presentation will cover the following aspects: the background and the motivation, then the contributions of this paper. After that, I will introduce the main idea of the construction. So let me introduce the background and show you what problem we have studied and why we studied. Sigma protocols are popular and widely used as a building block in many cryptographic protocols. Given a binary and a polynomial time relation and an instance xy belonging to R, the Sigma protocol is run between the prover and the verifier in 3 steps. A commitment, a challenge, and a response are sent in time by the prover and the verifier, where the challenge is randomly picked by the verifier. Finally, the verifier checks whether the transcript is valid or not. Sigma protocols have been designed to prove kinds of relations. Among these relations, K out of M partial knowledge is well studied. As early as 1994, Kramer, Danger, and Shoemaker showed a general method. In 2015, Gross and Kovacs showed how to achieve logarithmic communication when K equals 1. Very recently, Atema, Grammar, and Fair achieved logarithmic communication for general K and N in the discrete logarithm setting. A relation about K out of M partial knowledge can be expressed in disjunctive normal formula, and we call it complete K-DNF relations, since the number of the clauses is a binomial coefficient K over M. It's natural to consider some extensions. The first one is to reduce the number of clauses, and we call such relations incomplete K-DNF relations. The second one is to reverse the symbol of logic AND and logic OR, and then we get a relation in conjunctive normal formula. So we call such relations K-CNF relations. Our paper mainly focuses on K-CNF relations in the discrete logarithm setting. Relations expressed in CNF are an important collection of relations in practice. For example, many access control policies are naturally set in CNF, and they have been discussed in some ABE schemes. In addition, the instance of the K-set problem are expressed in CNF. We also provide a potential application here. A startup company wants to show the investors a business plan, which is about building at least a shopping mall in every K neighboring blocks. The startup company also wants to show it in a zero knowledge way in order to avoid the exact business roadmap being leaked. You can find the relation is also in CNF. To the best of our knowledge, we find the following schemes working for KCNF relations. The first one is proposed by Kramer et al. Here we call it CDS 94. However, it may lead to superpolynomial communication cost. The second one is a cyclicity program proposed by Eber et al. But it is designed for non-interactive zero-knowledge proofs, and it seems impossible to transfer a cyclicity program into a standard Sigma protocol. So it loses some advantages of Sigma protocols. For example, low soundness error by design, high efficiency, and more flexibility. Therefore, a question is raised naturally. Is it possible to construct a more efficient Sigma protocol for KCNF relations? Our paper gives an affirmative answer to this question in the discrete logarithm setting. Next, we are going to introduce contributions of this paper. The contributions of this paper are listed as follows. First of all, we formally define the partial knowledge of KCNF relations. We also propose a construction in the discrete logarithm setting by transferring the KCNF relations to directed acyclic graphics. That's why we call our method DAG Sigma protocol. Secondly, we apply our DAG Sigma protocols to construct Sigma protocols for incomplete K-DNF relations Due to the time limitation, we will not talk the details here. Finally, we provide an implementation based on elliptic curve groups. It shows that when proving the example relations in our experiments and combined with CDS94, our DAG sigma protocols saves more than 95% communication cost and more than 90% running time. Here is our theoretical comparison. To save time, here I only picked the comparison about KCF relations. You can see that the communication cost of our skin is big O n minus K element in group G and the big O absolute V element in group GP star. Note that big V denotes the vertices of the graph in our DAG sigma protocol. A discussion on upper bound of the number of the vertices shows that the size of our solution is smaller. Actually, is much smaller than that of CDS94, which implies our skin enjoys a better performance. Here are the experimental results. We firstly show the experimental result when K equals 4. The ratio shows how much communication cost and the running time our skin saves. It's clear that there is a remarkable improvement. These figures are the experimental result about different values of K. According to this experimental result, we can draw such a conclusion that when combined with CDS94, our skin achieves a remarkable performance improvement on proving KCF relations, no matter from the view of communication cost or running time. Next, let me introduce the main idea of our construction. Here is a formal definition of KCF relations. In short, every clause contains K different statements with logic OR. Then we combine these clauses with logic AND. A valid witness statement pair for such relation requires that every clause contains at least a true statement. In other words, for every clause, among the K statements, the prover knows at least one witness of them. Then we are going to introduce two building blocks. The first one is an algorithm, KCF to DAG. As the name implies, the algorithm is to transfer a KCF relation to a DAG. There are two properties of the DAG output by this algorithm. The properties guarantees the correctness of our skin. Firstly, every node in some path maps to a statement in some corresponding clause. Secondly, the number of passes with length K equals the number of the clauses. We take relation R1, for example. It contains 4 clauses, and each clause has 3 statements. Figure 5 shows a simple idea to transfer the relation R1, and you can find that there are 4 passes, and each pass maps to a clause in R1. In figure 6, we introduce 3 kinds of states with respect to the in degree and out degree of the nodes, and they are denoted as A, D, and E. We can merge those nodes which represent the same statement and has the same state. As a result, it's clear that figure 6 contains less nodes than figure 5. But the simple operation shown in figure 6 cannot work for some relations. For example, we present another relation R2. Combined with R1, R2 has 1 more clause. Here we marked it in red. Using the same method of figure 6, we get a result in figure 7. And the clause marked in red is transferred to the path with dotted lines. More exactly, the path is A4, B3, and E1. Then you can find that there is a crossing in figure 7. More exactly, there is a crossing in node B3. Then you can find other new passes. For example, A4, B3, and E2, which should map to a clause sigma 2, sigma 3, and sigma 4. However, we cannot find such a clause in relation R2. Therefore, the number of passes in finger 7 is not equal to the numbers of clauses of relation R2. Then it's contradictory to the properties we mentioned before. A solution is shown in figure 8. More exactly, the node B3 is divided into two nodes, B31 and B32. The example tells us that the DAG output by KCF2 DAG should not contain any crossings. In fact, the algorithm KCF2 DAG is simple and only contains 3 steps: preparing node, merging prefixes, and merging suffixes. For the details of the algorithm, please refer to our paper. Here, we take the relation R2 for example and show how the algorithm works. Figure 9 shows the first step. More exactly, for each clause in R2, we generate a pass. Then in figure 10, we show how we merge prefixes. Here, node A51 and node A52 are merged into one node A5. Similarly, node A41 and node A42 are merged into node A4. Figure 11 and figure 12 show how to merge suffixes. Similarly, node E11, E12, and E13 are merged into node E1. After that, the suffixes of the node B21 and the node B22 are the same. In other words, the suffixes are node E1. Then we can merge node B21 and the node B22 into node B2. Finally, we get a DAG and we can check that the DAG satisfies the properties we want. Here is the upper bound of the number of vertices. We can know one item is the binomial coefficient d divided by 2 over n. Note that in the original expression of a KCF relation, the number of statements can be k times number, where number denotes the number of clauses. The maximum of the number is the binomial coefficient k over n. Therefore, the theory implies that our method can achieve a good improvement. We also provide another method to analyze the upper bound in our full paper. Maybe it's easier for you to understand. First, we prepare two same subgraphies. The length of the passes in the subgraphies is k divided by 2. And the number of the passes in each subgraphy is the binomial coefficient k divided by 2 of n. Then for each clause, we divide the clause into two parts. For each part, we find the corresponding passage in the corresponding subgraphy, and we add an arrow between the two passes. Finally, we remove those passes with length k divided by 2. We can check that the DAG satisfies the properties we defined before, and is easier to get that the number of vertices is k times the binomial efficient k divided by 2 over n, which is similar to the result in our theory. You can find that in some cases, the result in our theory is a tighter bound. Next, we introduce another building block. It's a sigma protocol for 1 out of k partial knowledge in the discrete logarithm. The relation is shown in equation 3. In short, the prover knows at least one discrete logarithm of them. Then we recall the chameleon mode of the Snor sigma protocol. Note that in the standard model, the prover in the first step picks a random number r and computes the commitment using r. It's different in the chameleon mode. More exactly, the prover in the first steps calls us the simulator to generate the commitment. In other words, besides a random number r, the prover also computes the commitment using another random challenge, cpi. Here is our sigma protocol for 1 out of k partial knowledge based on Snor's Sigma protocol. The main idea is that for each statement, we compute the hash value or its commitment, and the hash value is the challenge for the next statement, such that we can call the simulator to generate the commitment for the next statement. One of the advantages is that the prover only needs to send one commitment of the K statements to the verifier. In other words, we only need to send A1 to the verifier. Therefore, we can reduce the communication cost a lot. Finally, we show our DAG Sigma protocol in the discrete logarithm using the above two building blocks. Here is the KCF relation in the discrete logarithm setting. And our DAG Sigma has two steps. The first step is to run the algorithm KCF to DAG and get a DAG. We can know that the length of each path in the DAG is K. So the second step is that for each path in the DAG, we run a proving algorithm, which is similar to that of 1 out of K partial knowledge. There are some differences between our scheme and the protocol for 1 out of K partial knowledge. In the 1 out of K partial knowledge, the relation is translated into one path with length K. The hash function only takes one commitment as input, as the corresponding node has only one arrow pointing to it. However, it becomes a bit complicated in the KCF relations. We're taking the relation R1, for example, and its corresponding DAG is shown here. We can find that there are two arrows pointing to node B2. Then, using the same method, we can know that the challenge for node B2 will be influenced by two commitments. In other words, it will be influenced by the commitment of node A3 and node A4. So the hash function takes as input the commitment of node A3 and node A4. Finally, in our paper, we proved that the DAG Sigma protocol provides computational knowledge soundness and is spatial HVZK. For the communication complexity, we proved that it depends on the number of the vertices of the DAG. And we showed that from the view of the communication complexity, our scheme is better than CDS 94. Here are some references of this presentation. That's all for my presentation. Thank you.
Thanks for the talk. Any questions? Okay, so it looks at when your protocol is turned into a non-interactive using a standard Fiat-Shamir heuristics, it looks like very similar to the one that you introduced in the early part of your talk, which is acyclicity programming approach. How do you compare those two approaches with respect to the non-interactive case?
Yes, exactly. Our method is similar to the acyclicity program. In fact, we combined it with our method in our papers, and the acyclicity program is designed for non-interactive zero knowledge, and we try to convert it into a standard Sigma protocol. However, we failed, so that we proposed the DAG Sigma protocol.
Okay.
Okay, thank you very much.
Any other comments, questions? Then let's thank the speakers and all speakers in this session. Thanks.
Thank you very much.